This is a help video for the Laplace Analysis Game in Circuit Tutor Level 1. Let's go ahead and launch that game. So we are presuming, of course, that you've already viewed the introductory tutorial on Laplace circuit analysis, which is under the heading of the Laplace impedance simplification game. Now, it's always a good idea to look at some examples initially before you begin to work the problems yourself, so I strongly recommend doing that. Here, in the interest of time, I'm going to go right into the game. Okay, so this is going to show us an example of a circuit problem here with two voltage sources and a resistor and capacitor and a sought voltage. And the first task, as always here, is going to be convert the time domain circuit, where we have farads and time and so forth, into the frequency domain circuit, where we only have ohms for all the impedances and S values. So to do that, we're going to remember that the Laplace transform of V2S here is 7u of t, so the Laplace transform of that would just be 7 over s, which we'll type down here. And if you don't remember any of the relevant Laplace transforms, you can always look them up in this table, but those common ones are probably good to know. Then the V1s of t, that's 4u of t, so that would just be 4 over s. And finally, for the capacitor, it's a 5 farad capacitor, very large one, so the impedance would be 1 over SC, which is 1 over, and we have to use the parentheses around the 5S there to make sure that it's all in the denominator. Okay, so having done that, then we just click the Done Converting button to check those conversions, and that is correct. And so it's going to replot the circuit now. And it's going to suggest here that we simplify the circuit so that we can use basically a type of voltage or current division approach, in this case voltage division, to solve the problem. So we're going to go into the circuit editor here before we try to write equations. And that'll give us some instructions here. And also some hints about right-clicking on elements and things. Okay, so what we can do here, of course, since we have two voltage sources, we can combine those since they're in series. And we notice that they have opposite polarities. This one has the positive side on the left, and then this one, if I'm going this direction, I find the positive sign here first and the negative sign here first. So those are fighting each other. This one is trying to make the current go in a clockwise direction, and this is trying to make it go in a counterclockwise direction. So we need to therefore subtract those two values. So the 7 over s minus 4 over s, of course that's easy to compute. That's just going to be 3 over s. And then the other voltage source, we want to make that 0 volts now, since we put its value basically into here. So that means it needs to be a short circuit. So we can either click this button here, or we can right click and choose short from that menu, whichever. Okay, so then we check that combination here with the check combination button before we do anything else, and that is correct. And that's as much as we need to do here to use voltage division, so I'm just going to quit at that point and click Done Editing. Okay, so at this point we can use our single loop analysis and do a voltage divider. So I'm going to select simply the sought branch voltage. If I tried to select other things here, it would really recommend that I do that. So we're just going to write an equation directly for V naught using the voltage divider formula, which for two elements would have this form. And so the source voltage here is the 3 over S value, the net voltage of the combined voltage sources. And also we notice that the positive side of that voltage source is connected to the negative side of the sought voltage V naught, and the negative side to its positive side. Therefore, it has different polarity, and that means we need a minus sign then to have the correct polarity. Or another way of thinking that is that this voltage source will make the current go in a clockwise direction. Therefore, the current will be going into the negative side of this impedance, which is active sign convention, which also reasons in favor of the minus sign there. Okay, so in the voltage divider, the impedance of interest goes in the numerator, so that will be our 1 over quantity 5s. And again, have to use parentheses there. And that'll also go in the denominator, so I'll just select that and copy and paste that down to the denominator. And then the other impedance, of course, is just the 7 ohms. So we have the sum of the impedances. So remember that the voltage source value divided by the total impedance of the series combination is going to give us the current, and that current multiplied by the SOT variable, by the impedance here, will give us the SOT variable of interest. So it's simply an example of using V equals IZ. Okay, so we'll check that now. And that is correct. And I'll say no more equations since we have all the equation we need. And now it's going to tell us we have to enter a final value for this quantity. And also, because we're going to be doing an inverse Laplace transform here to find V naught of t, which is the goal of our problem, it advises us that we need to factor any quadratic or higher order terms. Well, this one's actually not going to have that, so that's not relevant, but it's just a warning. Okay, so now in order to compute that, I'm going to show that on paper here. And so work that out here. So we have the minus 3s times the 1 over 5s times 1 over 5s plus 7. And to simplify that, of course, we want to never have fractions upon fractions. So we'll basically multiply both in the top and the bottom of this by 5s. And so that will just make this negative 3 on top, this constant over here. We have the s still. And then this becomes term 1, which I put over here, and then 5s times 7, of course, becomes 35s, which I've put over here. So I've written this in standard order. And then to facilitate putting that into partial fractions, we can also write it in this form. But for right now, I could just enter it this way. Well, actually, it would probably be a good idea to enter it this way because that'll prepare us better. It doesn't really matter, but I can do it either way. So I'm going to enter that as negative 0.08571 divided by, now I need to use square brackets to enclose the multiple terms in the denominator. So I'll have the s, which doesn't need parentheses, and then the s plus 0.02857. And to explain that, basically here I just wanted to basically normalize the coefficient of the highest power of s here to be 1, because that will put it in the form that's suitable for the partial fraction expansion. So to do that, I divide the top and the bottom by 35. So the 3 over 35 is just this fraction, and then this would be the 1 over 35ths here. And I could actually enter that as just 1/35 if I want to, if that's more convenient for you. So using a calculator, if you enter 1 over 35ths, basically it's going to tell you that it's going to convert that automatically to a decimal. And I'll only tell you that the first time it's doing it. So 1/35 there, and I could even have read this or entered this, for example, in the numerator as 3/35, so 3/35. And then get rid of that 1. And that will actually comply with order of operations since I'm using 2 division sign. So that would be fine. So I'm going to go, but I do need still the square bracket here. So I'm missing that square bracket on the end. So that completes the square brackets there, so everything's matched up. Okay, so now I can click check answers. And notice it converted into the decimal form anyway, which could have saved you the arithmetic, I guess. And now that's been printed for us. And then the next step is going to do the partial fraction expansion. So now I just select partial fraction expansion here since that's the only option. And we're going to need basically 2 terms since we have 2 different factors in the denominator. So I'll select both terms. Those are both going to have units of volts since it's a voltage here. So I'll just put that in both cases. The option is between amps and volts and watts, and this is all going to be volts. And then over here, I actually carry out the partial fraction. So I've written that in the form a over s. Since we have an s term, pole at the origin, and then b over s plus 0.02857. So that's a pole at the negative of that value. And now we'll use the heaviside method, or the method of residues, to compute those coefficients. So we can multiply through by the denominator of a, which is s. And then, having done that, there'll be an s here. We set s equal to 0 then. That gets rid of this term and just leaves us with a. And then the s here will cancel that s out. So that's not there anymore. Then I set s equal to 0. So that just gives us the upper constant here divided by the remaining constant here, since s is 0. And so just working that out, that's just -3, as you can see from the original fractions. And then for b, we do a similar thing. We multiply through by this denominator, and then we set s equal to the negative of this value, which then that will wipe out this term. So we just have b on the right-hand side, and likewise it'll cancel this term. And so we're going to have this constant here divided by the s value, which is now the negative of this constant. And once again, that's actually the same as what we had here, so the only difference is the sign. So this time we get b equal to +3. So fairly simple expansion. And now we'll just go ahead and put those numbers in here. So we're going to have a -3 over the s. And then the b term will be 3 in the numerator divided by the s plus 0.02857, and we don't need parentheses there because it's got its own text box, so it's basically automatically in the denominator. So now we'll go ahead and check the partial fraction expansion, and that is correct. That's been printed on the screen for us. And so now, since we've done all that type of equation, we just click no more equations, and it just basically tells us now we have to do the inverse Laplace transform to get back to the time domain. And so now we'll just select the only option there. And it's going to remind us that we do have 2 sets of terms here, which in some cases you might need. We won't need them here. But if you can't find the term you need, then you'd want to click on that extra menu to see those extra terms. Okay, so here I'm going to have the v naught of t. And then the inverse transform here, of course, of this would just be u of t, and this would be an exponential factor, which you may remember. If you have trouble remembering that, then you can look on the Laplace transform table available here. So I'm going to put in brackets so that I can enclose both of those terms and multiply them both by the u of t, which is necessary here. And so the first term will be the constant term for the u of s. That's going to multiply the u of t. And then the second term would be an exponential term for this one. And then we'll put in a closing bracket, and finally the u of t function that we always need to include. And that will also include the units, which is going to be volts, again, because this is a voltage. And now we just fill in the values here. So this is going to be, the constant is going to be -3 times the u of t, which is factored out. And then here we're going to have the coefficient of +3. And then the exponential, of course, should always be a decaying exponential, since this is basically like, something over s plus a. But we do need the reciprocal of that value, and that reciprocal of that value, I didn't show it over here, but that's 35. So we'll put a minus sign on the top, and that's going to be 35 seconds. And that completes the formula. So now we just check that. And that is correct. That's been printed for us. And let's expand that back out. And we're done with that. So we just click no more equations. It will generate a PDF transcript as always. And it's actually showing that here. So you can see your steps. And if you made any mistakes, they'd be shown in red here. And we can access that from the review work button on the main menu. So here I'm going to, and also you can see a detailed explanation if you like, showing the entire process, including the original simplification. So I'll just show that as an example here. It's going to look just like an example would look, basically. Okay, so there's the original circuit again, shows the conversion into the Laplace domain. Just scroll down there, and it shows the voltage sources being combined, explanation of that, and then all the explanation here. So if you weren't sure about anything, you can look at the explanation.